Second law of thermodynamics. This fundamental principle of thermodynamics describes the direction of spontaneous processes, the concept of entropy. Two statements of the second law of thermodynamics. Statement 1. Kelvin-Planck statement. It is impossible to construct a heat engine that can convert all the heat energy put into it into useful work with no other effect. Also known as the Kelvin-Planck statement. It is impossible to build a heat engine that can convert all the heat energy into useful work without any losses. It means if heat taken from hot body is heat taken equals input equals Q1. Some of the heat energy will always be wasted. Heat wasted equals Q2. Output equals increment W equals Q1, Q2. The efficiency. Equals output slash input times 100%. N equals increment W slash Q1 times 100%. N sad face Q1, Q2 slash Q1 times 100% N less than 100%. Efficiency of a heat engine will always be less than 100%. Reason. Q2, Q1. Statement 2. Clausius statement. Heat cannot spontaneously flow from a colder body to a hotter body without any external work being done. Delta S equals delta Q slash T. The change in entropy, delta S, of a system is equal to the heat transferred, delta Q, divided by the temperature, T, at which the heat is transferred. Also known as the Clausius statement. It highlights A. The direction of spontaneous heat transfer. B. Heat will always flow from a hotter body to a colder body, and not the other way around, without any external work being done. C. This means that it is impossible to build a refrigerator that can transfer heat from a colder body to a hotter body without any external energy input. Both statements equivalent. One. Describe the same fundamental principle of thermodynamics. 2. They both tell the idea that spontaneous processes, such as heat transfer, always occur in a specific direction. 3. It is impossible to build a machine that can violate this direction without any external energy input. Applications. One. Various industries, such as power generation. 2. Refrigeration. 3. Air conditioning. Clausius statement MTH. Form. Delta S equals delta Q slash T. The change in entropy, delta S, equals the reversible heat transfer, delta Q, divided by the temperature, T. Delta S, universe, equals delta S, system plus surroundings, greater than or equal to 0. Increment S greater than or equal to 0. The total entropy change of the universe is always greater than or equal to 0. Important slash examples from real-world applications are power generation. The equation. T. It is used to calculate the entropy change of a power plant, which is essential for determining the plant's efficiency. Refrigeration. Delta S equals delta Q/T. The entropy change of a refrigeration system, which is needed the system's coefficient of performance. Air conditioning. The equation. Delta G equals delta H, T delta S. It is used to calculate the change in Gibbs free energy of an air conditioning system. Carnot heat engine. The Carnot heat engine. A. A theoretical thermodynamic cycle. B. Proposed by Nicholas Leonard Sadie Carnot. C. Era/year. 1824. D. Ideal heat engine. The Carnot heat engine is an idealized heat engine that operates on a four-step cycle. 1. Isothermal expansion. T1 equals constant. Absorbed heat equals Q2. Adiabatic expansion. Q1 equals constant. Temperature decreases. 3. Isothermal compression. T2 equals constant. Q2 equals heat released. 4. And adiabatic compression. Q equals constant. T increases. Carnot heat engine parts. 1. Hot reservoir. A high-temperature reservoir that provides heat to the engine. 2. Cold reservoir. A sink/low-temperature reservoir that absorbs heat from the engine. 3. Working fluid. A fluid that undergoes a cycle of expansion and compression, transferring heat from the hot reservoir to the cold reservoir. 4. Piston and cylinder. A piston and cylinder assembly that converts the thermal energy of the working fluid into mechanical energy. Cycle of the Carnot H. engine processes. 1. Isothermal expansion. The working fluid expands isothermally, absorbing heat from the hot reservoir. T1 equals constant. He absorbed equals Q1. 2. Adiabatic expansion. The working fluid expands adiabatically with no heat transfer and the temperature decreases. Q1 equals constant. Temperature lowers. T1 2. T2 equals constant. Q2 equals H air released. 4. Adiabatic compression. The working fluid is compressed adiabatically with no heat transfer and the temperature increases. H.E equals Q equals constant. T2 1. During complete cycle. Input equals Q1. Output equals increment W equals Q1. Q2. Efficiency CH engine. Eta equals output/input times 100%.
EQ1, EQ2, Q1 100. E1, EQ2, Q1 100. E1 από τη 2, T1 100.
Let T2 equals 0 K.
E1 0, T1 100. E1 100. E100 100. E1.
Where eta is the efficiency, T2 is the temperature of the cold reservoir, and T1 is the temperature of the hot reservoir. Importance of the Carnot heat engine. The Carnot heat engine is important because it establishes the maximum efficiency, the fundamental limit imposed by the second law of thermodynamics. Theoretical framework. The Carnot heat engine provides a theoretical framework for understanding the operation of real heat engines and for optimizing their design. Influence the development of thermodynamics. The Carnot heat engine influenced the understanding of the relationships between heat, work, and energy. Thermodynamical efficiency. The factor with Q2 is called as T.D. efficiency. It is denoted by eta and gives the fraction of the heat taken from the high-temperature reservoir, which it is possible to convert into work by a heat engine. The efficiency of a Carnot engine, the most ideal of all engines, is controlled by the operating temperatures of the engine. The larger the temperature difference, T2, T1, between the high and the low temperature reservoirs, the more the heat converted to work by the heat engine or vice versa. ET. For a given temperature of the high temperature reservoir, T1 equals constant. The lower the temperature of the sink, the greater will be the efficiency of the machine. Similarly, for a given temperature of the sink,